Hello everyone, I am Harika Shinde from Institute of Aeronautical Engineering and from Computer Science and Engineering branch. Today I am here to share and present my AAT concept video of a course Data Structures. My topic is Time Complexities of Binary Search and Interpolation Search. Let's begin. First, what is time complexity? In computer science, the time complexity is a computational complexity that describes the amount of a computer time it takes to run an algorithm. Time complexity is commonly estimated by counting the number of elementary operations performed by the algorithm. Supposing that each elementary operation takes a fixed amount of time to perform. Thus, the amount of time taken and the number of elementary operations performed by the algorithm are taken to be related by a constant factor. Since an algorithm running time may vary among different inputs of the same size, one commonly considers worst case time complexity, average case complexity, worst case time complexity, which is the maximum amount of a time required for inputs of a given size, less common and usually specified explicitly. Average case complexity, which is the average of the time taken on inputs of a given size. This makes sense because there are only a finite number of possible inputs of a given size. In both cases, time complexity is generally expressed in the size of the input. Since this function is generally difficult to compute exactly and the running time for small inputs is usually not consequential, one commonly focuses on the behavior of the complexity when the input size increases. That is the asymptotic behavior of the complexity. Therefore, the time complexity is commonly expressed using big O notations, typically big O of n, big O of n log n, big O of log n, big O of 1, big O of 2 power n, big O of n power alpha, where n is the size in units of a bits needed to represent the input. These are the different and a variety of ways in which time complexity is usually expressed. Algorithmic complexities are classified according to the type of functions appearing in the big O notation. For example, an algorithm with time complexity big O of n is a linear time algorithm, and an algorithm with time complexity O of big O of n power alpha for some constant alpha is greater than 1 is a polynomial time algorithm. Next, binary search algorithm and time and space complexity. Now, in this PPT, we are going to see, in this slide, we are going to see about binary search algorithm, time and space complexity. First, what is binary search? Binary search is one of the searching technique that works efficiently on a sorted list. Hence, to search an element into some list using the binary search technique, we must ensure that the list is sorted. Sorting is generally done on the basis of ascending order or a descending order. Binary search follows the divide and conquer approach, in which the list is divided into two halves and the item is compared with the middle element of the list. If the match is found, then the location of the middle element is written. Otherwise, we search into either of the halves depending upon the result produced through the match. Now, here it is the algorithm of a binary search. First, binary search, we define binary search, a lower bound, upper bound, and value. First, in step one, we assign set begin to lower bound and end to upper bound and position to a -1. We repeat steps 3 and 4 if beginning is less than or equal to end. Now we are defining here mid. Mid equals to beginning plus ending by 2. If a mid equals to value, we simply return a position of a mid value. Otherwise, we go to step 6. Else, if a mid is greater than value, then we print mid -1. Else, beginning mid plus 1. end of loop. Okay, if position equals to 1, then print value is not present in the array. Step 6, exit. It just terminates the function and returns exit. Binary search complexity. Now let's see the time complexity of a binary search in a best case, average case, and worst case conditions. We will also see the space complexity of a binary search, time complexity, case time complexity. In best case, the time complexity of a binary search is big O of 1. In average case, the time complexity of a binary search is big O of log n, whereas in worst case, it is big O of log n. Hence, best case complexity in binary search, best case occurs when the element to search is found in a first comparison, that is when the first mid element itself is the element to be searched. The best case time complexity of a binary search is big O of 1. Average case complexity. Average case time complexity of a binary search is big O of log n. Worst case complexity in binary search, the worst case occurs when we have to keep reducing the search space till it has only one element. Worst case time complexity of a binary search is big O of log n. Now coming to space complexity. Space complexity is big O of 1. Space complexity of a binary search is big O of 1. Now concluding here, we can say that best case complexity of a binary search is big O of 1, average case is big O of log n, and worst case is big O of log n. Here are the time complexities of a binary search in a various cases. Now, interpolation search, its algorithm and time complexity. In a typical English dictionary, now here we are going to find first what is interpolation search and its algorithm. In a typical English dictionary, data is a quite uniformly distributed. For example, all the words starting with A or B will be in the ending, will be in the beginning of the dictionary, and all the words starting with Y and Z will be in a very end of the dictionary. On the other hand, words starting with the M and N will probably lie somewhere in the middle. So angle, so it follows the order angle. As it starts with the A, it will be put in a first place. Then coming to binary, it starts with a B, so it can be put in a second level. Now again, the word starting with the M and N will probably lie in the middle. So the last two words will be word starting with a Y, and last word will be word starting with a Z. So angle, binary, and yesterday and zoo. Names in a typical English dictionary are sorted in an increasing order. Now, so if we want to search a word like binary, the natural human instinct will be to start the search in the beginning of the dictionary, because we know that ways all the words starting with a B must lie. On the other hand, if we want to search for a word like zoo, you might start in the search in the latter half of the dictionary. To simplify, it doesn't always make sense to always start in the middle of the data set. Rather, we can start our search at different positions each time based on the element we need to search. Since the data is uniformly distributed, the probability of finding the element near a specific position will be higher. The above example is a principle on which interpolation search is primarily based. The human instinct to find an element in a uniformly distributed sorted data set. Algorithm. Initialize n equal to size of array. Now we are assigning low equal to 0, high equal to n minus 1, that is size minus 1. We will use low and high to determine the left and right end of the array, in which we will be searching at any given time. If low is greater than high, it means we have exhausted and the array and we couldn't find k. We return -1 to signify that the element k was not found. If k is less than array of low divided by k array of I, it means k is either less than the smallest element or greater than the largest element of a current array. And since the array is sorted, we will never be able to find k in this array. Hence, we written -1 to signify that the element k was not found. Now, else if low is greater, less than or equal to high, we apply the interpolation equations to find the index, where we should start the search form as follows. Initialize index to low plus k minus array of low into high minus low divided by array of high minus array of low. If array of index is less than k, sorry, it means the element at a current index is less than k. Thus, all the elements in the left side of the index will also be less than k. Hence, we repeat step 2 for the right side of the index. We do this by setting the value of low equal to mid plus 1, which means we are ignoring all the elements of a from low to index and shifting the left end of the array to index plus 1. If array of index is greater than k, it means the element at the current index is greater than k. Thus, all the elements in the right side of the index will also be greater than k. Hence, we repeat step 2 for the left side of the index. We do this by setting the value of high equal to index minus 1, which means we are ignoring all the elements from the index to high and shifting the right end of the array to index minus 1. Else array of index equals to k, which means the element at the current index equal to k, and we have found the element k. Hence, we do not need to search anymore. We return the value of index directly from here, signifying that index is the position at which k was found in the array. So that was the algorithm for a interpolation search. Now we are going to see about time complexity of an interpolation search. Let's start. If the data set is sorted and uniformly distributed, the average case time complexity of an interpolation search is big O of log 2 of log 2n, where n is defined as a total number of elements in the array. On the other hand, if the data is sorted but quite normal randomized, the time complexity of an interpolation search will be much worse than binary search. In fact, it will be almost similar to linear search, that is big O of n, capital N, where n is defined as a total number of elements in the array. Now, space complexity. It's quite evident that we are not using any significant extra memory in an interpolation search. So, the space complexity is constant, that is big O of 1. The variables used for storing the bonds, index, and other minor informations are constant, since they don't depend on the input size of the array. So thank you. This was my AAT concept video of a course, data structures. Thank you.